All right, good morning. I guess I don't know what time it is for you, but I'm recording this in the morning, which is unusual for me. Welcome to another Stat 510 video. In this video, we're going to talk about convergence of random variables. And we sort of hinted at, but not made explicit, this idea that when we get to statistics, statistics can be viewed as random variables. And a question that we'll often sort of ponder is, what happens with more data? And often, the answer to that question, hopefully, is something along the lines of, well, our statistic becomes better. That is, statisticians, we always rant and rave about, we want more data, we want more data, we want more data. Well, our methods and the statistics we're using had better improve with more data, and especially not get worse with more data. We'll sort of return to that idea when we discuss statistics and estimation, finally next week. But for now, we're just going to talk about, well, I have a random variable. What happens or a sequence of random variables, what happens as n gets really big, that is, the sample size grows. Okay, so we're going to talk about two main ideas. There'll be a bunch of definitions and theorems along the way, but basically we're sort of highlighting two main ideas here. The first is called the law of large numbers, which essentially is going to say that with high probability, the sample mean is close to the true mean. That's rather intuitive, but we actually have we can be specific about when that's true and sort of how it's true. And then the next main idea, which is sort of a central idea, is called the central limit theorem. And what it says, we're going to state it much more specifically, but for practical purposes, it says that x bar n is approximately normal. And these two statements I just said, implicitly, these are true. We need to be more specific for them to be true. But in general, the notion is when n is large. And here we're going to talk about like letting n go to infinity. But for practical purposes, maybe in previous courses, you've seen the central limit theorem used to say, approximate a probability about a sample mean when n is quote-unquote large, where large is sort of context dependent, and we'll talk about that a little bit in this video. Okay. First definition we're going to need. So we're sort of going to be working in this setup where we have a sequence of random variables, say x1, x2, and so on and so forth, and then some other random variable that we'll call x. And the notion that we're going to define here is the notion that xn converges in probability to x, which we will write like this. Something like that. And that is true when we have some epsilon. I need to remove myself. Bye. Where is that? Okay. Bye. See you later. Okay. So the definition here, we have this probability statement for any epsilon. It goes to 0 as n goes to infinity. So the way to think about this is here we're looking at the difference between xn and x. And the probability that the distance is bigger than some error, we'll call it, that goes to 0 for any epsilon. And so the idea is that we could let epsilon be as small as we want. It doesn't matter how small. So the probability that we make an error bigger than that goes to 0 when n goes to infinity. So essentially this is this notion of, well, eventually a realization from xn and a realization from x, they'll have to be very close together when n is large. Okay. So a similar but subtly different definition is called convergence in distribution. So here we roughly have the same setup. Now we're just going to note that we'll use f sub n to denote the CDF of xn and f to denote the CDF of x. And now we're going to talk about xn converging in distribution to x, which I will write like this. This is one minor deviation from the text. The text uses a squiggly arrow, and I'm just not going to be good at writing that. So I'm just going to use an arrow with a D over it for convergence and distribution. And this is the case when the CDF of x sub n, the limit of it, is equal to the CDF of x for values where f is continuous. And that'll be a subtle point that we'll note in an example in a second here. Okay, so I just wanted to pause here to note that when we're thinking about the possible distributions of this random variable x that we're converging to, one particular type of distribution comes up fairly often that's sort of important to think about. And sometimes you might not even think about it as a distribution because there sort of is no distribution in some sense, but it is a distribution. And that's what we call a point mass distribution. So here we have some random variable x, and we say the probability that x is c, some constant, is 1. So that means it only takes one value, and it always takes that value. Sometimes instead of writing, when that is the case, when the x that we're converging to is one of these point masses, instead of writing x sub n converges in probability to x, we will sometimes write x sub n converges in probability to c, and similarly for distribution. Where is that? Okay, like this. Okay, so they're saying the same thing, but sometimes it's nice to make it clear that we're converging to a point mass and not, say, a distribution with multiple possible values. Okay, minor note there, but it's kind of subtle, but it'll come up a few times, and it is actually important. Okay, let's look at an example that will hopefully highlight the difference between, using these two definitions. Okay, so our setup is going to be, we have some sequence of random variables, and we'll denote them x sub n, and they are normal with mean 0, and then some variance which decreases as n increases. And sort of intuitively, I think we probably have this notion that, well, it's going to converge to 0, right? So, the mean of this distribution of the xn's is 0, but the variance is getting smaller. So you can sort of think of the distributions almost collapsing to a single point, 0. So, but let's prove that, or not prove, but just show that's the case both in distribution and in probability. So we'll have a notion of like how that's happening. So first we'll look at distribution. So I guess I'm sort of giving it away here. I'm immediately going to define f to be the CDF for a point mass at the point 0. So that CDF looks like this. It's 0 for any value for any x less than 0, and then there's a jump at x equals 0. So maybe it looks something like this, right? So here's the point 0. So that's the CDF that we're working with here. So I'm also going to note that if I multiply x sub n by zn, I then arrive at a standard normal distribution, and that'll just make thinking about some probabilities easier here. Okay, so I'm first going to consider the case where t is less than 0. So, and I want to look at the CDF of these xn's when that's the case. So first I've just written the definition of a CDF. And then I'm going to multiply by square root of n on both sides. I'm actually going to move this over just a bit to give myself more room. Okay. So this is equal to the probability square root of n times x sub n less than or equal to square root of n t. Okay. And we said that, well, that thing is then standard normal. So we get something like this. Okay, and now let's think about this for a moment. So remember, we said that t here is less than 0. So that's negative. And then what we're thinking about doing is letting this n increase to infinity. So I think it's pretty clear if we consider the probability that a standard normal is less than some value that is pushing closer and closer to negative infinity because t is negative and n is getting bigger, well, then this thing goes to 0. Okay, great. So, and then if we move to the t is bigger than 0 case, I think you can maybe see right away that we're going to get a very similar thing. So I've skipped a few steps here, but now this t, remember, t is bigger than 0. We let n go to infinity. Well, so this probability then is going to go the opposite direction, and this is going to go to 1. So then I can conclude and say that f sub n of t, that goes to f sub t when n goes to infinity. Therefore, x sub n converges in distribution to 0. However, I've been just a tad bit sloppy here. We should probably note that we don't need to worry about t is 0. So what I've written so far is true when t is not equal to 0. And why can I do that? Well, let's consider the case when t is 0, right? So, well then the CDF of xn at that point 0, it's 1/2, right? Because we're dealing with a normal distribution, and the probability that a standard normal is, the probability that a normal distribution with mean 0 is less than 0 is exactly a half. It's a symmetric distribution, and that is clearly not equal to f of 0. F of 0, which we define above, which would be 1. So here we have an example of the CDF of xn not being equal to the CDF of x, but that's baked into the definition here. We only need it for t where f is continuous, and we've pretty clearly shown here we have a discontinuity at x equals 0. So we don't need to worry about that. Okay. So now we've shown that it converges in distribution. How about in probability? Well, what am I going to do here? So I will... so this is the probability that I want to go to 0. And if that's the case, that would be exactly what we needed here. Let's see. So I think what I'll do is I'll multiply both sides of the inequality inside of that probability statement, and I'll square them. Boy, I just rambled there. I don't know even what I said. Anyway, so now that I have this, I can apply Markov's theorem. And turns out that this is then equal to the variance of x sub n divided by epsilon squared. And recall that's because the expected value of x sub n is 0. So the expectation of xn squared is exactly the variance of xn. And this thing then, sort of from the problem statement, we get 1 over n divided by epsilon squared. As n goes to infinity, pretty clearly that's going to go to 0. Therefore, we have x sub n converging in probability to 0. All right. So maybe the important example here is talking about an example when we have convergence in distribution, but not convergence in probability. So it's not the case that if we have convergence and probability, it's not the case if we have convergence and distribution that we automatically get convergence and probability. So here I have an example. We're going to say x is just standard normal, and then xn for any n is negative x. So I think it should be fairly clear that x and xn simply have the same distribution. Okay, just to make that overly clear, if we look at the expected value of x sub n, well, that is sort of by definition -1 times the expected value of x, which is 0, which is 0. And the variance of x sub n would be -1 squared times the variance of x, which is 1, which is 1. And then when you have a nice linear transform of a normal random variable, you get another normal random variable back with these expected values and variances that we just found. So they have the same distribution. So it's sort of trivial to say the limit as n goes to infinity of f sub n of x is equal to f of x. Therefore, x sub n converges in distribution to x. Okay, so that wasn't too bad. What about convergence in probability? So here I have the probability statement that I would like to show goes to 0 as n goes to infinity, right? But remember, negative x sub n is just negative x, so this probability statement becomes, that's not the color I want. Let's do blue. So this is the probability that 2 times x is greater than epsilon, which is then the probability that the absolute value of x is greater than epsilon squared. And now we have a probability about some normal random variable being greater than some, arbitrary value. I can't tell you exactly what that probability is unless you tell me epsilon, but I can tell you that it's not 0. So therefore, convergence in probability, no, it does not. Okay, so let's think about this a little bit, though, because I think this is a bit of a subtle point, and this is one of those things that took me a long time to sort of really grasp. So, as the name suggests, convergence and distribution cares about distribution. That's not particularly helpful, but that's the truth, right? So in this example, it's very clear that x and x sub n have different. They have the same distribution. It's just exactly the same distribution. But if I randomly sample a value from x, or I should maybe say if I randomly sample a value from x sub n, I immediately know the value of x. It's just the negative of it, right? So there's a huge dependency between these things where a random observation of the two is going to be wildly different. And that's what this probability statement at the bottom here essentially says. And that's where convergence and probability is different. Because the way I think about this is, well, what we're really doing is say, I want to randomly sample a value from x sub n, and then I want to randomly sample a value from x. What's the probability that they're, close together? Except in this case, again, we've defined x sub n to be, just completely dependent on x. So, and the way we've done that, the values are going to be far apart. So, the way I think about this is convergence and distribution cares about distribution. Convergence and probability cares about, well, if we sample from these two different things, are the values going to be close together? Subtle difference, but as we see here, it can make a difference. Okay, another quick definition. So we can say that xn converges to x in quadratic mean, which we will denote like this. If this statement we have here is true. And now you might sort of be thinking to yourself, well, why do we have so many different notions of convergence? Well, here's one reason why. So here we have statements about how these things relate to each other. So the first one says here, if we have convergence and quadratic mean, well, then we get convergence and probability. Often we're interested in convergence and probability, but sometimes it can just be a little easier to work with convergence and quadratic mean. So show convergence and quadratic mean, and then you get convergence and probability. Great. Similarly, we get, if we have convergence and probability, we get convergence and distribution for free. However, what we just showed here on the previous slide is that the reverse, or I guess I say the reverses of these things, are not true in general. But what we can say, this third bullet point here, is if the x is a point mass distribution and you have convergence distribution, well, then you do get convergence and probability. So that is the reverse being true, but again, that doesn't always happen. Okay, moving on. Here's a slide with a lot of notation. Let's just talk about this really quick. So here we have a sequence of random variables xn and some x, a sequence of random variables yn and y, and then g is some continuous function. Okay, so what we have here is examples of, for example, the first one, if xn converges in probability to x and yn converges in probability to y, well then xn plus yn converges in probability to x plus y. These are probably pretty similar to some limit theorems you saw in calculus. I want to highlight a couple of these though. So here, this one and this one, these results that mix convergence and distribution to a random variable and convergence and distribution to a point mass, these are together called Slutsky's theorem. And sort of similarly, the last two results, which deal with either convergence improbability or convergence distribution, and then applying a continuous function to these things, these are called the continuous mapping theorem. But generally, these are all theorems you would use if you already have a convergence result or two and you're looking for another result that is dependent upon those two. Well, you might be able to mix them together, apply one of these theorems, and get the result that you're looking for. Okay, so now finally to one of our main ideas here. Okay, so what we have now is what's called the weak law of large numbers. There's also a strong law. We're not going to talk about that, but it is in the appendix of the book if you're interested. But for the weak law, we have this setup where we have x1 through xn, which are IID, with the mean of these things all being mu. So this is pretty close to that classical setup, but we actually haven't said anything about the variance yet. When this is the case, the weak law of large numbers says that the sample mean x bar n converges in probability to that mean of each individual x. Okay, so to prove this, I'm going to be a little bit lazy and make the proof easier by assuming that the variance is finite, but note that that's not technically a condition of the weak law, and we could prove this without it. It's just a lot more work, so we don't feel like doing it right now. But anyway, here's the probability statement we need to converge to 0, and then we apply Chebyshev's, and we get something like this. And then just knowing what we know about the variance of a sample mean, we get something like this. What is it? N epsilon squared, and we get an n in the denominator. We're a big fan of when that happens, and this goes to 0. There we go. Okay. Right. So just to think about this for a second more before we go on. Essentially, this says, well, the more data we get for the sample mean, the closer it gets to the true mean. And isn't that nice? that'll come up quite a bit. Okay, so the other main idea, which I'm guessing many have seen before, is this notion of the central limit theorem. And sometimes it's a little bit confusing. The central here is not about means, at least to my knowledge. It's about the fact that this is a very important limit theorem that's very central to everything we do. But you could remember it either way. So here we are now we're going to live in the very classic setup of we have x1 through xn, which are IID. They all have mean mu. They all have variance sigma squared. We define the sample mean the usual way. We then define this z sub n to be sort of the standardization of x sub n, which we can write a couple ways here. And then when that's the case, this converges in distribution to a random variable z, where z is standard normal. Okay, cool. So that's pretty useful. So that says that the sample mean is, in a limiting sense, standard normal, and that will have some practical purposes. So one thing that you've probably done with the central limit theorem before is used it to make approximate probability statements. So you could look at a statement like, well, what's a probability that the sample mean is bigger than some number? Well, it's approximately normal, and now we can calculate it even if we don't know the actual distribution of x bar. And we'll say things like, well, this is true for any distribution of xi, and we'll say that this is true when n is large. And I just want to be careful here. So first of all, and to denote that, I'll put not smiley faces, not frowny faces, but sort of just like neutral faces here. So for any distribution of xi, well, no, there's actually some conditions on it. So for example, if the xi's were Cauchy, this would not work. We have to, anything is true with the right conditions. And so for this statement to be true, we need the conditions laid out here to be true. I should note that there are other slightly different versions of the central limit theorem, but this is the one we're talking about. We're following the book in this case. Okay. There's also the statement when n is large. Well, we got to be careful there, right? So anytime we're approximating a probability, that's sort of living in practice where, well, we have a finite data set, but we're saying that the n is very large here. Therefore, x bar must be sort of approximately normal. But, notice when we're talking about convergence and distribution, we're talking about letting n go to infinity. So there's sort of a difference between infinity and a finite value. And that's why we're saying we can approximate this. But we have to be careful and realize that the approximation is just that. It's an approximation. And it depends upon things like how big n is, which we're saying large, but what is large? And then we should realize that large is dependent on the distribution of these xi's. So many xi's satisfy these conditions here, but we need to be careful about sort of how abnormal that distribution is. So say the more skewed that distribution is, the larger n we need for this probability approximation to hold. Okay, and so when we're thinking about approximating these probabilities, you might see all these various other ways of writing this. I just want to note that, like, for me, thinking about it this way is sort of much more natural. I don't know why this one just sort of like sticks in my brain more so, but I want to note that it's important that we wrote the convergence and distribution on this slide the way we did, where on the left-hand side of the convergence are all of the n's, but on the right-hand side there's nothing dependent on n. So it would be a little odd to try to claim convergence and distribution here, because now you have something on the left-hand side that's dependent on n, but also now something on the right-hand side that depends on n, but you just told me n was going to infinity. So that's just something to be a little bit careful about. But if you're using the central limit theorem to say, well, I'm going to approximate a probability when I have an n that is very large, well, then you can use all of these sort of alternative rearrangements. But to apply the central limit theorem properly, you need to make sure you have standardized the sample mean. Okay, right. So later on, when we get into, say, things like building confidence intervals, we might want to sort of utilize this limiting normal thing, but and then rearrange and make a probability statement about the distance between like x bar and mu, but we won't know sigma. So we need to have a central limit theorem that works with replacing sigma with Sn, that is the sample standard deviation. And it turns out that you can do that. And why can you do that? Well, you're going to tell me because we're going to use proof by exercise. So you'll need to show this on the homework this week. So yeah. So we're talking about the using this idea to approximate probabilities. Well, a natural question is, well, how good is the approximation? Well, here you go. It's exactly this good. Or sorry, not exactly. It's at most this good. So anyway, what we have here is a theorem that tells us how good that approximation is. So under certain conditions, so this won't work for all cases where the central limit theorem applies, but if we have certain conditions met, then we can make a statement about the biggest difference between the sorry, oh gosh. I'm going to take a swig of coffee real quick here. The difference between the CDF of Z sub n and the true standard normal CDF. And again, when all those conditions are met, we can bound this above by this sort of crazy looking expression, which includes a hard-coded 33/4, but it's dependent on n here. So with different n's, we can understand how good this approximation is. But I would note that if this is a little bit daunting, it seems like more work than it's worth. What I would say is maybe try simulations. So you'll be limited to the exact simulation you're looking at, but maybe generate some random variables from a particular distribution. Calculate the sample means and look at what happens as n gets bigger and how far away it is from the normal distribution that we're using to approximate it by. That'll also get you sort of an intuition about how far off these things can be. Okay, so one last note here, something called the delta method, which says that if we're in this situation where we have a yn, which we can standardize, and then it converges in distribution to a standard normal, and g is some differentiable function where it's not 0 at one particular point of the derivative, well, then we have this new expression which also converges to a normal distribution with mean 0 and variance 1. Except you can't see that because I didn't write it. I'm looking at my notes, not what I'm writing actively. Okay, and then sort of similar to the central limit theorem, we can make a statement like this. So if yn is approximately normal, mean mu variance sigma squared over n, then if we apply g to that function, g to that random variable, then it is also normal with some new mean, which was a function of the previous mean, and then this new variance, which we see how to calculate here. Okay, so that's a little bit about convergence of random variables. Again, so this sort of wraps up our discussion of, our very quick discussion, probably not too detailed discussion of probability, just to sort of get us in the right frame for moving on to statistical inference, which is going to be the remainder of the course. We're going to dive in right away next week and sort of both overview it and talk about then one specific thing. And then that'll just sort of be what we're talking about the rest of the time. Right. So, as always, if you made it to the end of the video, good job, and I'll see you in the next one.